All right, welcome to this explainer. I am absolutely thrilled you're here today because we are going to crack one of the most notoriously tricky yet incredibly satisfying dynamic programming challenges out there. I'm talking about the 0-1 knapsack problem. If you've ever stared at a coding challenge and just felt completely stuck on how to optimize it, well, you are in the exact right place. We're going to break this whole thing down visually, step by step, until the logic completely clicks for you. To really understand the math here, we first need to set the stage. Picture this high-stakes scenario. You're a thief inside a store. You've got a tiny backpack, your knapsack, and it can only hold a very specific amount of weight. Now, the store is packed with items, and every single item has its own weight and its own dollar value. Your ultimate goal: you need to walk out of that store with the absolute maximum value possible without ripping your bag. It's the ultimate dilemma, right? Balancing extremely limited capacity against maximum reward. Okay, let's dive into this. Here is our roadmap for mastering this challenge. First, planning the store heist. Then, why obvious plans fail. Third, the dynamic programming solution. Fourth, populating the DP table. And finally, optimizing the getaway. Starting off with Section 1, planning the store heist and analyzing our constraints. Let's ground this abstract coding problem into reality. Imagine our backpack has a strict maximum weight capacity of exactly 7 units. We'll just call that cap equals 7. Surrounding us are our target items. Let's label them 0 through 3. Notice how item 0 is worth a massive $70, but it weighs a hefty 5 units. Meanwhile, item 3 only weighs 1 unit, but it's only worth $10. Every choice we make here requires a sacrifice of our precious capacity. Now, if we look really closely at the numbers, we can actually manually figure out the optimal solution for this specific setup. The absolute most valuable combination we can fit into our backpack at the exact same time are items 1 and 2. Item 1 is worth $50 and weighs 3 units. Item 2 is worth $40 and weighs 4 units. Put them together and they perfectly hit our maximum weight constraint of 7, maximizing our total haul to exactly $90. You might be wondering why this is officially called the 0/1 knapsack problem. It simply refers to the binary all or nothing choice we have to make. For every single item on the shelf, you've got exactly 2 options. You either completely pack it into your bag, that's a 1, or you completely leave it behind on the shelf, that's a 0. You can't just break a TV in half and take part of it, right? It's a pure binary decision. Moving right along to Section 2, why obvious plans completely fail us, looking at brute force and greedy algorithms. So our first instinct is usually the brute force approach. You might think, hey, why not just generate every single possible combination of items and see which one makes us the richest? Well, because of that binary choice we just talked about, evaluating every item creates an exponential explosion of possibilities. If you have n items, you get 2 to the power of n combinations. If you're robbing a large store, your code will literally be running until the end of time. It's just way, way too slow for a clean getaway. Okay, what about our second instinct, a greedy algorithm? A greedy approach just says, grab the most expensive item first. Sounds logical, right? But if we do that, we grab the $70 item. The catch is it weighs 5 units, leaving us with only 2 units of capacity left in the bag. The only other thing that fits is the $10 item. Boom, our total haul is $80. But hold on, we already proved earlier that the optimal combination is $90, so going the greedy route literally leaves money on the table. Let's get into the real meat of this in Section 3, the dynamic programming solution. This is our master plan. To solve this elegantly, we need to approach it mathematically. We're going to define a core recurrence function, and let's just call it knapsack. It takes 2 parameters, I, which represents the index of the item we're currently looking at, and cap, which is the remaining capacity of our bag. This function is basically asking one very simple question. What is the absolute maximum value we can achieve starting from item I with this exact remaining capacity? To find the answer for any given item, we essentially have to look at the 2 parallel universes of our subproblem. We have to calculate what happens to our total value and our remaining capacity if we include the item, and then compare that against what happens if we exclude the item. The larger of those 2 outcomes, that's our optimal choice. Let's break down both of these universes. Let's look at option A, our inclusion branch. If we decide to take item 0, awesome, we immediately gain its value of $70. But actions have consequences. It weighs 5 units, so we have to subtract 5 from our starting capacity of 7. This means we're now left to solve a brand new, slightly smaller subproblem, finding the maximum value of the remaining items, starting at index 1, but now with a tiny remaining capacity of only 2. Now contrast that with option B, the exclusion branch. If we decide to skip item 0 entirely, well, we gain 0 valued right now, but we get to keep our full untouched capacity of 7. Our new subproblem in this universe is finding the maximum value of the remaining items, starting at index 1, with our full capacity of 7 still totally intact. By evaluating both paths for every single item, we absolutely guarantee that we never miss the optimal combination. Section 4. Populating the DP table. Let's see how we track all these subproblems. To store our calculated answers so we aren't constantly repeating our math, we create a 2D dynamic programming grid, basically a table. This table has 2 dimensions. The rows represent I, our current item index, and the columns represent C, our current knapsack capacity. But to fill out any table systematically, we have to establish our starting points, our base cases. When do we know the answer without having to do any of the heavy math? So the crucial point here is how we anchor our entire table with zeros along the edges for those base cases. Think about it. If you look at the top columns, if our capacity is 0, we can't fit anything in the back, right? So the max value is just 0. And looking at the bottom row, representing index n, which means we've totally run out of items to even choose from, the max value is also 0. An empty bag holds no value, and 0 items yield no value. These zeros form the solid foundation we build everything else upon. With our base cases locked in, the algorithm is actually super straightforward. Step 1, we start way at the bottom of the table, at row I equals n minus 1, meaning we only consider the very last item. Step 2, we iterate through every possible capacity column from 1 all the way up to our max capacity. Step 3, we just work our way upwards row by row until we've considered every item up to index 0. And here's the genius part. Because we're working bottom up, every single time we need to look at a subproblem, its answer is already saved in the row below. Picture the actual execution path of our algorithm. We're sweeping from left to right, bottom to top. By checking the previously solved cells right below us, we completely avoid all those redundant, time-wasting calculations. And the absolute best part of this whole process, once we finish filling out that top row, our final, perfectly optimized maximum haul is going to be waiting for us right there in the top right cell, DP00 cap. Finally, Section 5, optimizing the getaway. Let's reduce that complexity. Let's do a really quick complexity analysis. Our time complexity is incredibly solid at big O of n times cap, simply because we visit each cell in our grid exactly 1 time. No exponential nightmares here, which is great. However, our space complexity is also big O of n times cap. Because we're generating and storing this entire 2-dimensional matrix in memory, it can get a little bit bloated if we're dealing with thousands of items in a massive capacity bag. But wait, let's look at how this builds into an incredible final optimization twist. Think back to the math we just discussed. To fill out any cell in the current row, the formula only ever needs to look at the values saved in the 1 row directly below it. It never looks 2 rows down. It never looks 3 rows down. That means we don't actually need to keep the entire grid in memory. We only ever need to store 2 one-dimensional arrays, the current row we are filling and the previous row we just finished. This one simple realization brilliantly slashes our space complexity down to just big O of cap. And just like that, my friends, you've completely cracked the 0-1 Knapsack problem. You dodged those exponential traps, you utilized dynamic programming to track optimal substructures, and you even optimized your space complexity for a perfectly clean getaway. As you walk away today with your maximum haul of knowledge, I want to leave you with this provocative thought. Now that you know exactly how to identify these parallel include versus exclude universes, where else can you apply this pattern of optimal substructures to simplify the really complex challenges in your own code? Keep building, keep learning, and I'll catch you on the next explainer.